Welcome to session 8 of Introduction to Productions Management, OMIS 302. Today we'll look at transportation models. Now, transportation is an awesome part of production. Now, if you look back in typical life experiences, no firm produces in the market. Now, wherever you produce, you would have to transport whatever you produce to a certain point of distribution to your end user. Now, transportation would not only be considered in that external case. Even within the organization where production is undertaken, transportation goes on. In between departments, unfinished or semi-finished items are transported in between departments, and that's some idea of transportation as well. So generally, transportation models just helps us understand how a firm can transport its finished item or finished good from one point, we'll call it a source, to another point, which we'll call it a destination, in the most or the least costly manner. That's what basically transportation models are. So we're going to look at techniques of how we can, undertake transportation. So basically, transportation models is we'll refer to it as a minimization technique. So we are either trying to minimize cost or we are minimizing distance. You want to use the shortest possible path or the shortest possible route to your destination, or if that is not an option, then you want to use the least cost possible. You want to incur the least cost possible in transporting your items from your source to your destination. So we say consider a scenario where a company with 3 warehouses. So let's say A1, A2, A3. So the warehouses from the diagram are on the left, and then intends to transport a single item to 4 demand centers, say B1, B2, B3, B4. So you see, it is possible that the item could be from A1, let's say from warehouse or source A1, could be moved to point B1 or B2 or B3 or B4. In the same as B2, the same as source A2, we can also move from B1, B2, B3, B4, and it goes on and on like that. Now, you do not necessarily have to supply all the destinations from one source. So we want to look at how do we achieve this kind of movement in the least possible manner. So this is just a diagram or a pictorial view of what transportation is talking about. So here we could be looking at cost, we could be looking at the distance and other things. Now, you're saying that a typical transportation model is formulated for a class of problems with the following characteristics. So before we can use this technique we're talking about, we want to look at some let's say some conditions preceding how we use this technique. So a product is transported. So for now, we are looking at single products. We're not looking at multiple products, just a single product. So you produce an item and you want to transport it, that same item either from multiple warehouses to multiple destinations, but not multiple items. So a product is transported from a number of sources to a number of destinations at a minimum possible cost. Each source is able to supply a fixed number of units of the product, and each destination has a fixed demand for the product. Now, you see, you need to understand this second point in the sense that now if you were producing, you would want, because we want to minimize costs as much as possible, you would want to ensure that what you are sending from one source to one destination should just be the exact, not even in excess of 1, because whatever excess comes at an additional cost. And so if market A requires 100 units of whatever item you want to transport, then you make sure that you are supplying exactly 100 units to that market, given all your analysis that you have done. I hope you understand. Now, so if you transport 101 units, whereas they need 100 units, you're going to transport an extra unit there, which will be at an extra cost, and you may have to return it to your warehouse or your source. Again, that will also come at an extra cost. So we want to ensure that ideally the total supply must be equal to the total demand. Whatever you're supplying at the end of the day should be equal to the whatever is being demanded in total. Now, in this case, the problem is regarded as a balanced transportation problem. So whenever we are looking at any transportation problem, where if we put together all the demand of all the centers and then the supply of all the warehouses that you have, we sum these two and it's the same. You have, let's say, 2,000 units to supply and the demand required is also 2,000 units, then that type of transportation problem is required or is referred to as a balanced transportation problem. Now, there could be instances where your demand could exceed supply or your supply could exceed demand. Then in that case, we say we have some unbalanced transportation problem. And we also have, we can deal with both as well. But for now, for the purposes of this study, we'll mainly look at what balanced transportation problems, and we'll just walk you through how we deal with the unbalanced transportation problems as well. Now, in every transportation problem, there are two major steps. Now, for our transportation problems, we do what we first call arriving at or finding our basic feasible solution. Now, the basic feasible solution is to say that, how you just do your allocations at the least possible cost to meet all the demand and then exhaust all your supply. Now, when you arrive at your basic feasible solution, well, you cannot tell whether that solution is actually the optimal or the most efficient or the least cost solution. And so the second stage is what we call the optimal solution, where we test the basic solution to see whether indeed that solution is the best or we could have an opportunity of improving on that solution. And so for the basic feasible solution, we say that the transportation problem requires two-stage approach to arrive at the best and optimal solution. Okay, so the first stage, to identify our basic feasible solution, there are three techniques that we have. We have one we call the northwest corner method. We also have what we call the least cost method. And then the third one, which is the Vogel's approximation technique, which we call VAM. But we will discuss just the northwest corner method and then the minimum cost. Now, the idea is that the reason why we would not look at the Vogel's approximation method is that, well, it's more like when you use the Vogel's approximation method, whatever you tend to get at the basic feasible solution turns out to be the optimal solution. In fact, let's say in 99% of the time, you get it. So because it is very scientific and it contains a lot of iterations. In fact, it is more complex than the first two that we are going to see. And so probably all the lapses that we do not take care of in using the northwest corner method or the least cost method, the Vogel's approximation technique kind of takes care of all that. And so your basic feasible solution turns out to be your improved solution. And so for that reason, we will not look at but we'll look at the northwest corner. And then, so let's first look at the first one. So typically, we represent our transportation problems in the matrix or in the table form, where we have the demand points at the top and we have the supply on the left side of our table. Okay, so you see we have B1, B2, B3, B4, which are our columns representing the demand centers. And then we have A1, A2, A3, which are the supply units or the supply centers, which are on our left. So those are on the rows. So the columns represent the demand centers, the rows represent the supply centers. Now, if you look at this, we're saying that A1 has a total supply of 40. A2 has a total supply of 60. And A3 has a total supply of 50. Now, B1 requires a demand or requires units of 20. B2 requires 30. B3 requires 50. And B4 requires 50. Now, when you sum your total demand, you see 50, 50, that's 100. 30, 130 plus 20, it makes it 150. If you sum up the supply as well, we have 50, 60, that is 110 plus 40, that's another 150. So you see, your total demand and then the total supply are the same, and that is the 150 there. So in this case, we would say we have a balanced transportation problem. Now, in between these, you have some cells in there with some numbers written in there. So you have one cell highlighted and you have 4 in it, then by 8 you have 6, 8 in that order. Those values you find in there are the unit costs of transportation, so the per unit costs. So we are saying that if I'm going to move from A1 to B1, it will cost me, let's say, 4 cedis. If I'm going to move from A1 to B4, it will cost me 8 cedis. If I'm going to move from A1 to say, A2 to say B3, it will cost me 6 cedis, in that order. So those values you find in there are the per unit cost of transportation. So let's look at how we go through the northwest corner method. For the northwest corner method, to arrive at your basic feasible solution, what we look at for is, if you look at the table we have here, let me go one step back. Now, here, this table looks quite clean and nothing has been done to it yet. So let's spend a little time here. Now, this table here, see the cell that has been highlighted, or you see the borders being deepened, that cell in that row down to A3, those are the cells that we are going to do the allocation in. Now, you want to look out for what we call our northwest corner cell. And the northwest corner cell is always the cell in the top left corner, which is what we have highlighted in this case. Okay, so if you find your northwest corner cell, you consider the demand and then the supply. So you see, the northwest corner cell occurs in between A1 and B1. Now, then we can say it is in row 1, column 1. So it is in row A1 and column B1. Now, B1 requires a demand of 20. A1 has a supply of 40 to offer. So we have said initially that you give exactly what is demanded, right? You can't give more than what is required. And so if A1 is willing to offer 40, but B1 requires 20, then we would allocate as much as possible in that cell, considering the demand and supply requirements. Now, demand is 20, supply is 40. So what is the highest, or the highest possible allocation we can make in that cell, A1, B1? Think about it. Demand is 20, supply is 40. So I'll give you 3 seconds. Okay, I bet you got it right. So we can only allocate up to 20 units because demand point B1 requires only 20 units, but A1 has 40. So we'll give it all the 20 it requires.